So what we are actually going to see is we are going to see how the backpropagation network is going to help neural network to increase its prediction accuracy. That's what we are going to see. In a neural network, we have a special feature called as an activation function, which in turn acts on the neurons to model the weights actually. So let us first understand what is the backpropagation. We know what is activation function, why it is used, everything. Very simply, if I want to say, this activation function, its major role is to increase the weighted values prediction and make some nonlinearity in my model. So we know, right, many activation functions are there starting from identity, sigmoid, tanh, then binary, then ReLU ramp. Many things are actually available, right? Let us first see that. And now we are going to see how backpropagation can be used. How what is feed forward, what is backpropagation, everything we'll be seeing in this particular class. And the main motto is understand the very mathematical model of this backpropagation. We should understand clearly what is happening in that hidden layer. That is what the main motto is. So let us first see the definition of backpropagation. So backpropagation is nothing but it's a supervised learning algorithm only. So we entirely NN is actually a supervised learning algorithm where backpropagation is again a supervised learning model which is used during training the neural networks for training neural network models, right? Just for example, we have something like a hidden layer. We have an input layer, hidden layer, as well as the output layer. So what actually happens is I'll be having layers such as, say, I'll be having the neurons. Say I have these neurons, and say this is going to be my input, and my input will be I1, I2, and so on. Let me have two inputs, say I1 and I2, right? I'll be having those inputs. So let me try to draw a typical neural network model, and we can use the same model for doing our mathematical summations and so on. Right? We will see a sum also in backpropagation, and to understand how exactly the activation functions work, how exactly the gradient descent is used, everything we'll be seeing here mathematically, right? So this particular layer I call it to be hidden. So I say this is going to be hidden layer one, H1 and H2. I'll be having H1 and H2. H1, decrease the font. H1, and this is going to be H2. And finally, I'll also have an output layer, so which actually performs, actually gets the predicted value and stores it. So this is going to be my output layer. Okay, let me call it the outs one, right? I'll be having something as an output layer, that is output. Now there can be any number of interconnections here. Those interconnections are actually being trained by my model only. It's not the developer going to train it. It is actually trained by the model directly. So how it is actually directed also, starting from an input layer to an output layer, it will be flowing out. So I'll be starting from, say, I1, it will be going to some H1, and I can have many such things. So I1 can also go to H2. Similarly, this is I2. Now I2 can go to H1 and H2 and so on. That is a hidden layer models. Can go to the subsequent hidden layers. So many such interconnections can be there. As long as the number of interconnection increase, it means that my model is going to predict as keen as possible, or it is going to learn as deep as possible. That's what I can also have several layers like that. Those layers can also be interconnected to give me a better model. But here, to make it simple mathematically, even this is actually not simple because we need to use some gradient descents over here. So let us first learn the mathematical model by using a single hidden layer, and then we will proceed to multiple hidden layers, and when we go into the practical sense. Okay, this is what we goes. In addition to these, I can also have some other thing. What is that? That is called as a weight, the hyperparameter, the actual thing which actually makes my output to be somewhat accurate. So I say this is going to be W11 because it is moving from input 1 to hidden layer 1. So I call it as W11. Right, this is W11. And I'll have, and this is will be W21. Okay, this is W21. And this is W12. So these weights we are going to calculate now, and we are going to understand how the backpropagation network is going to use those kind of thing and increase the accuracy. We are going to see that. We'll have W22. And similarly, I can also have something over here, the weights. I can call these weights as, this is going to be the output layer. So from, I can call it as, if I cannot call it as W11 again, I can call it as W10, sorry, one out. I can call W1 out, and this is W2 out. So these are the weights I actually have. Initially, some random number can be given to these weights, or initial training can give some random values to these weights. But obviously, we know that if I substitute some weight values here, then surely my output will not be correct. Right. So we'll be checking now. What is we have to do is now we have to understand what is the feed forward network. Feed forward is nothing but I have these I1 values from input. I'll be substituting some output values. Sorry, I will be substituting the weight values going to the hidden layer and going to the output. I mean, I was going in the forward direction. That is actual machine learning algorithm. I can also have some bias over here. Those bias also I can include. Those bias can include either H1 or H2 or any passes can have its appropriate bias. Those also I can include. So bias also is actually plays a key role here. I can include bias if needed. And another RMO that comes from B1 and B2, we know why bias is used. And we can also have a learning rate along with that. Now, what is backpropagation? So that is actually the thing, the key requirement for us to understand. If I move from the input layer to the hidden layer and from hidden layer to the output layer, this output layer may ask me some particular result, but surely I will not be in a position to say that the exact result is obtained. From I1, I'll be going to I2, and I may not get the exact result what I actually require. I may require some different result. I get some different result. So what I'll actually do now, I'll be doing something to train my particular output values that I call it as backpropagation network. Now I again need to go back, check what is the difference between the target output and the actual output. What is actually obtained by me and what is the target variable. So this is actually target, the actual and the expected value, and what is the actual obtained value. Both I will actually subtract. Based on that, I will be doing some calculation. So I'll be calculating the error for this. I'll be calculating the mean squared error for this. So once I calculate the mean square error, next I can actually go back and train these W values. I need to modify these W values in such a way that I can get some different results. So that in the next iteration, this should be somewhat reduced. So this is actually called as backpropagation. Going back, calculating the weights one more time, and then predicting the output again. This is what I actually call as the backpropagation network, right? The thing to understand here is, if I increase the hidden layer also, I can get some good results. But if I increase the hidden layer, surely my complexity will also increase. So what I should actually do is, I should use some gradient descent mechanism and try to reduce the error as low as possible. I need to use some gradient descent mechanism so that I can reduce the error first as low as possible for this particular hidden layer. So what is my motto now? It will be now, we have to use the weights and along with the neurons. By neurons, I call these circles as these nodes, along with the neurons to predict the outputs. if the actual value and the obtained value are close and the error is minimum, then our task is done. Then our task is done. We don't have any other task. Else, what we have to use? Else, we have to go for back propagation to find the better value for the weights. To find the better values for the weights. So that's what we are going to do. So initially we'll be doing it. Then what? How I can find the better value? We use the gradient descent mechanism to understand how the weights actually differ. We're using the gradient descent mechanism to find the global minimum error amongst several iterations that we in neural network model we call it as epoch. Across several epochs I can actually do. So I can actually repeat the same step again and again. In which epoch I get the lowest error, I stop that particular error. Or in which particular epoch I get the maximum accuracy, what I actually expect for in that particular epoch, I can stop. So to find the global minimum error amongst the several iterations or epochs. So this is what we are going to see. Right? I understood why we are going for back propagation. Am I making it clear? The main concept why we are going for back propagation in neural networks. Am I making it clear? Yes, shall we proceed?
Yes, sir.
Yes. Now let us go to a mathematical problem. Now we can use a particular problem to identify how to calculate those weights, how to use back propagation, how to use gradient descent. Everything we are going to see using a mathematical model, right? Problem on back propagation. So let me take these diagrams for me so that I don't need to draw it one more time. Let me have two outputs for my problem. It is a two-way classifier. Yes. So we have something like this. And in addition, I can also have bias. Usually, whenever a neural network model is given to you by the institute or by it is actually trained by you, usually it will come along with some bias. So we can write it along with the bias also. This bias will be somewhat small, actually given for a particular purpose. To satisfy a particular purpose, we can have that bias also, acting on the particular network, whatever we want. So those networks, I can include some bias. It is not mandatory also, but it is usually required when you want to shape your model accordingly, what you actually expect in the output. Because everything cannot be expected directly from the model. For something, you require some bias. So for that, you can use it. You cannot believe for the weight alone to do everything. You can also add some external bias. So that's why I'm adding here. So there will be bias for every weight it is going on, right? That is the intercept, the y-intercept concept. So I'll add those things also. Now let us give some values for each of the weights we have. So for those weights, these are actually the random weights. Assume that model has understood by in the initial training. Say for example, for this, the weight the model has taken is say 0.15, and for this say if the model has taken some 0.20, and for this say the model has taken 0.20 again, and for this the model has taken say 0.30. We have the 0.20, so I'll change 1 to 0.25. So 15202530. And similarly over here you can have some. we have here, that is 0.40, and one more, this is from H1 to, and this is out 1 and out 2, we have to name it that out 1 and out 2, and this is 0.40, after that 4 5 or 50, and we have H2 to output 2, that is say 0.45, and finally we have another bridge, that is say 0.55. And bias, I set the bias to be 0.35 over here, and another bias is set as 0.60. So we have the intercept also ready. So if needed, I will name this as B1, and this is B2, the bias, right? So this was the question given to us. Now output also will be given. What will be the first output and what will be the second output? The actual outputs will also be given to us, and based on that, we need to train our model. Say this is going to be output 1, value going to be 0.01. That's what I actually expect from the model. What it should be is say 0.01. That's what I expect from my model. I can write it outside better. 0.01, and this output say 0.99. And I also assume that the individual hidden layers is going to use some sigmoid activation. So it is going to use a sigmoid activation over here, the same like a logistic classifier, right? Now let us go on and train this model by using some backpropagation network. For this particular model, we are going to use the backpropagation network. How to use, right? Now I ask you a simple question, right? We can also we didn't name this input layer. The initial input what we obtained is 0.05, and this particular input is 0.10, right? These are the two inputs we actually obtained, right? Now what is how H1 can be calculated? Can anyone say how H1 can be calculated? H1 is I1 into W1 plus I2 into W2. Am I right or wrong? Can you understand how H1 can be calculated? Can you understand how H1 can be calculated? Yes? Yes, answer me, please.
Yes, sir.
Yes. So let us calculate the H1, H2, everything. I'll go for the solution. We'll calculate the individual hidden neurons. H1 can be calculated as I1 into W1 plus I2 into, this can be written as, this is W11, that is from 1 to I1 to H1, and this is I2 to H1, so I2 into W21, right? So what will be the result? This is 0.05, so 0.05 into, what is I W11? W11 is 1 to 1, that is 0.15 is the weight. So what is the value here? 0.15 plus what is I2? 0.10 into what is W21. What is W21? What is W21?
0.20.
So what will be H1 value totally? Zero point zero five into 0.15 plus 0.02. Am I right? This is right. The H1 value 0.22 is the H1 value. Am I right? Yes or no? Now what we are actually doing is now we have calculated the direct weights. Now we can include the bias also. So when I include bias, my H1 value can also increase because I'm also having a bias which is actually coming for that 0.35 value. So my bias is actually having some 0.35 value that is also contributing to H1, right? I also should include that 0.35 also. So include that 0.35. What will be the total value now? So I'll include the bias plus B1 also should be included. So plus 0.35. Can anyone say what is the total value of this? What is the total value?
0.57.
0.57, right? 0.57. I to get the same in the calculator. So I just multiply everything and then I get the result, right? Nothing actually different. Just to get, this is feed forward is actually very simple. We don't have any big calculations and all. Everything is very simple, right? Now what I do is I actually name this as a different word called net H1. This net value of H1, I name this as net H1, right? Similarly, can we calculate net H2? So I will go and calculate the net H2. H2 can be, how H2 can be calculated? Can you say how H2 can be calculated? How H2 can be calculated? 0.05 into what?
Zero point two five.
Is 0.05 into 0.25 plus 0.05 into 0.25 plus, or we can write the formula. Can you say the formula? I'll write the formula first. What is the formula? I1 into W12. This is 1 and this is 2. So I1 to H2. So W12 should be there. So I1 into W12. Then what is the next one? What is the next one? Say quickly. Say quickly, pa.
I2 into W22.
I2 into W22. Good. And we also have to include the bias. Right? What is the bias value? Plus again bias 1 is actually doing here. So we will be substituting the value 0.05 into 0.25 plus 0.10 into, and what is the W22 value? I'll see. W22 value is 0.30 plus bias 0.35. Calculate the answer. What is net H2? What is net H2? I'll also calculate. Right? I'm getting 0.3925. Is it correct? Is it correct? Shall we proceed with 0.3925?
Yes,
That
sir.
is, yes, 0.3925. 0.3925 are the individual weights for that. What is this? Is only 0.57 or any other extra value came? 0.05 into 0.15 plus 0.02 plus 0.35. Oh, this is actually 0.3775. No one said me. Abhiram, have you checked this, Abhiram?
Yes, sir. Checking. I'm checking for net hedge.
Yes. Shall we proceed for O1? Shall we proceed, pa?
Yes, sir.
Yes, sir.
Yes. So the answer is 0.3775, right? Yes. Now we can go for O1. Now say the formula for O1 quickly. Don't make a more delay, but quickly say the answer. We have less time. Let us finish this feed forward at least. How to calculate O1?
H1 into
H1 into H1 in
W
H2 into W 2,
W
2
2
output
output
plus bias 2. So let us go up. Somebody see the value and then say me. H1 we have down itself. This is 0.40. This is 0.45. This is 0.65. 404565. So H1 is 0.3775. This value H1. I'm taking this net H1 value into what is that 0.40
40.
plus 0.37. What is the H2 value? 0.3925 into 0.45. I hope plus 0.65 bias. So bias also obtained. Now we'll be using these values to calculate the total. So what will be the total now?
0.977625.
0.9776. Okay, should I have
25.
like, okay,
Okay, sir.
2 is actually 4 digits. Right, O1 is calculated. Is it sure, right?
Yes, sir.
Right, shall we proceed with this O1? Right? Yes, okay, now we got this. Now the value, my value is just 0.01, but the actual value say it is actually being 0.97. So surely it is actually not applicable. Now what we use is, now I use an activation here. I use an activation here because directly if I give the H1 to O1, then there will be no difference between the machine learning and the neural networks. So surely what I have to use is I need to use some activation. Why? Because this H1 value I will not range from 0 to 1 alone. This H1 will be H1, H2 may also go greater than 1. So surely I need to make them reduced to a value between the range 0 and 1. So I need some activation. So the activation what I'll be going for is the logistic activation function, that is sigmoid function. So what I will do is using some logistic function, using a logistic activation. Using logistic function, let me reduce the range of H1 and H2. Or let me make the H1 and H2 to be somewhat different so that it can, the output can be calculated. I do not calculate output directly with these weights. Instead of using these weights, let me calculate the output by using a logistic function instead. If now see the difference how the logistic function is going to give, because see the difference 0.01 is here, but the obtained is around 1. Heavy difference is there. So surely we need to do something, right? So first I go for a logistic function. So now a different way of calculating O1. So what I will actually use, we know the logistic function is 1 divided by 1 plus e power minus x. That is the sigmoid function. We'll write that. Let me take the equation so that formatting will be good. 1 divided by 1 plus e power minus, I'm going to use the net H1 to calculate the output H1. I'm not going to take the influence of H2 directly. So let me see how out H1 is going to be there. So I'm not going to calculate directly the O1. This is actually the effect of from H1 alone, or if you need it, I can also name it as output from H1. This can be output through H1 alone. What will be the output? I'm going to calculate by using a logistic activation function. So what will actually come is, I use here something, the net H1 value I'll use here, net H1. I'll substitute everything here. So the net H1 value what I actually have here is 0.3775. 0.3775 is my net H1 value. So if you can you find the answer for this? 1 divided by 1 plus e power minus 0.3775. I have this computer calculator. If I go to the scientific mode also, yes, E is there. So I have to calculate e power 0.3775 e plus 1 is equal to 3.7182. 1 divided by 3.7182, I get 0.26. Don't know whether I have to take e power minus. I hope I have taken plus minus 0.3775 is this, and the e of this is this plus 1 0.37182. 1 divided by 0.37182, 2.689. I hope this is also not right. Can anyone calculate in the scientific calculator and say me? 1 divided by 1 plus e power minus 0.3775. Actually, I have the answers here separately, so I'll write directly for time needed. It is 0.5932. Right, Abhiram, can you calculate this if you have scientific calculator? Abhiram?
Yes, sir, I'll try.
Yes. So now see the difference. And I'm not saying that output one is calculated. First, I change the value of H1 by being 0.3775 to this 0.5982. So I just increased the value of H1. Similarly, I can actually calculate for out H2. Out H2 by using the same logistic classifiers, I can do that. So instead of H1, I can use here H2. And instead of e power minus 0.3775, my H2 is 3925, and I'll get the answer as the slight difference is 0.5968. That's the answer. Viram, have you checked the answer for both? Viram, have you checked?
Yes, sir, correct.
Yes, fine. So now instead of using this, we have to use this because activation is actually required when we go for a neural network criteria. If you didn't use activation, then there will be no difference between the normal learning algorithm and how the neural networks actually performs. So now after activation, you take this as your new H1 values, and now you substitute the new H1 values here instead of this H1 values. This will be out H1 and out H2. So instead of these values, you substitute your new values. 5932, and this is 5968. Now you calculate what is the total value. It will be around some 1 point something. It will be the new value. What is the new value? What shall I use? So instead of Abhiram, everyone can actually try so that we can finish it quickly. Sujita, what is the new value? 5932.
1.1558, sir.
1.155. 1.1558. So similarly, we have to use for O2 also. So O2 is here. So for O2, what are the things coming? 0.50 is coming, 0.55 is coming, and bias 0.65. 50 and 55 is going for O2. So I'll calculate O2 now by using the same formula. These formulas I can use. So out H1 from W1 to out 2, and out H2 from W2 to out 2. So these are the things I will use. So this is 0.50 and this is 0.55. That's it. I am right? 0.50 and 55. Now what will be the answer, Pa? 1.3748. Okay. Now again apply the logistic function. Apply logistic function for the O1 values and find the final O1 values. Out O1 is equal to 1 divided by 1 plus e power minus O1. That is actually the output, final output of O1. So apply the logistic function and then find what is the final O1 value by using the activation. So this is the O1 value what I actually obtained, that is 1.1558. I need to apply to the logistic classifier and then I have to find the actual output value. What is that? Instead of the O1 I can substitute here minus 1.1558, and for out O2 I can calculate the same 1.2748. So what will be the total value now after applying the logistic function?
0.7605, sir.
0.7605 for out O1, and for out O2 I think this also will be in 0.7 because closer values only are 0.6. What is the value here?
0.7816.
7816. Fine. Now we got the output one and output values. Now let us see what is the actual value required. Actual value required is 0.01 and 0.99. But the obtained O1 values are 0.7605 and 0.7816. So it is actually a huge difference between what is actually required and what is the total. So let us find the total difference in the errors. So what is the error from output 1? That is, I have to now how many outputs are there? There are two outputs. So if I want to take the mean square difference, then I should take 0.01 minus 0.7605 the whole squared, and I should again take 0.99 minus 0.7816 whole divided by 2 items are there, so I need to take the mean, so whole divided by 2. So initially itself I'll take this as 1 by 2. So I'll write the thing target minus the output, that is out over. So what is be the target minus output over? 1 by 2 into 0.01 minus 0.7605 the whole squared, and error O2 will be this 1 by 2 because there are two output cells. So if I want to take the mean, so it is divided by 2. That is why the difference is like that. So calculate and say what is EO1 and EO2. This is 0.99 minus 0.7816. What is EO1 pa?
0.2816.
0.2816, and over here this is actually somewhat lower than this. This is
0.0217.
0.0217. So this error is somewhat low, this error is very high. We need to work on this. What is the total error now? Total error, or I can take it as E total. Add both and say E total is equal to 0.0217. 2816 plus 0.0217, which will be 0.3 something, right?
0.3033.
0.3033. Now we have to use, now for forward network is completed. Now we have to use back propagation to reduce this 0.3033 by modifying the W1 values, right? We will continue the back propagation in the subsequent class.